Yeah. First, what's the problem? So if you know set theory, if you study set theory, you know that there's this very hard exercise to prove that. So we have a partial order on a set. We have a certain set Q, for example, and we have a partial order. Then actually there is another order for the stress, which is bigger and which is linear. Okay, linear meaning like every two elements are comparable. Okay, it's Sorn's lemma. I think it's called actually Shapiro-Line theorem anyway. So very, very easy result. Okay, how can we make it less easy? We can throw some additional structure. Okay, let's throw some additional structure and things become more interesting. So instead of an arbitrary set, let's consider a group. So let G be a group. Okay. And now we have another order, like just order on group. And we say that the order is invariant, for example, left invariant or right invariant if it's invariant under the multiplication for the corresponding side. Okay. So it means like, for example, left invariant order, let's check like that, right invariant order or right invariant order. Invariant. What does it mean? It means A is smaller than B implies AG smaller than BG for okay. Yeah. Very easy. And we can ask a question, is it possible to extend a partial right invariant order to a linear right invariant order? Okay. Very usual question. And now this question becomes much more interesting, of course. So much so, I think that it will not resolve yet completely, for which groups is actually possible. Okay. And what is known is that, like first theory, it's a theory by Rentoul and Forman. They did it independently in the 70s. If G is, I think it's locally important and torsion free, then we have this huge problem. Okay. And what they also show, at least Rentoul didn't from my paper, that there is a counterexample, very easy counterexample, which is some Metabelian group actually. So there is a Metabelian group for which we do not have such extension property. Also, make note that I said torsion free, obviously torsion free is the is an important requirement because otherwise we just cannot have a linear order, linear invariant order, because we have like a vicious circle. So yeah. And I think I don't know actually whether something apart from this is no.
Sorry, can you recall what linear is?
Linear means total. Like linear total is I use it interchange for that. Yeah. So just any two elements for comparison. Okay. So now let us think about maybe another formulation of the same thing, for which we will need maybe some definition. So first, if you have a set Q, we define the order Q. There's a set of all partial orders. Okay. And T order for Q. All total orders. Okay. So if Q happens to be a group, then we have an action on these guys. Okay, actually two actions what we fixed. I think here it's more convenient to have a right action. So for example, on the order of G, and the action is like this. So A G smaller than B is equivalent to A G smaller than B G. So what it means? So we have this space of all partial orders in the group. Okay, we want to define what is the action. So we take the partial order, which is here, and want to define what is like what is the result of applying G to this order, and this is the definition. Okay. So indeed, this is a left action, like very nice. So what we have actually is a topological dynamical system. If G is, for example, is a countable group, so we can handle this guy with product topology, because what is partial order? But partial order is just a relation, so it's just a certain subset of 2 to the G times G, so we can handle it with counter-sect topology. Okay, and this is like a close subset. Okay, and now we say that invariant random order on G is an invariant measure, where here, okay. Invariant measure here is invariant random order. Okay. And okay, so there are some examples. Like first example is we can take a partial invariant order, put a delta measure there, and this becomes an invariant delta measure here. Okay. Another example is we take a kind of uniformly invariant order. Like there are many like at least two constructions, one of which is we take our group, we take an independent Bernoulli process which takes values in the unit segment, 0, 1 segment. And so we assign to each group element independent random variable. And then we just take an order corresponding to the order of those variables. Okay, and so we have a uniformly random linear order, and it's like easy to check to be invariant. Okay, so yeah. Now we want to define kind of extension property for these guys. Okay? How can we do this? What we can do, we can define another object. So we have P ord partial orders, total orders on the set. We also define a bit more complicated object. The space of all order extension pairs. What we have as said, the space of all order extension pairs is the space of all pairs of order such that one is partial order on our set, and another is a linear order on the same set, such that it extends our first order. So we have one order partial, maybe of course linear, another linear, and this linear order extends the partial order. Okay. So now what is it? Is it just actually just a subset of product keyword times keyword, okay? And of course here, yeah, so also I would like to note that this is also a closed subset. And here, invariant under the action, here G. And so what we get kind of get an action of G on or next. The three order extension pairs. And as I said, it is a subset of the product, okay, the OR and the OR. And so of course there is a factorization to the partial orders to the first coordinate. So we have two coordinates here, partial order, linear order. We just forget about the linear order. And so here we also have a match. And it's easy to check that it is actually a factorization of dynamical systems, like we have a confusion diagram. And the question is now, is it true that for any invariant measure here, meaning any invariant partial random order, we can find a measure here, so kind of it is both a linear order and the joining, what is called joining, which connects these guys, such that projection of measure here is our initial measure here. So definition. We say that G has IRO extension property invariant from the model extension property. If for any new invariant measure on the board, there exists new invariant measure on that. Such that projection on the board of U is new. Okay. Okay, does make sense? So what is it is actually an instance of like a very classical problem. So we have one topological system, another, a factorization, and just an instance of a measure lifting question for topological systems. Whether it's possible for a given factorization of topological systems to lift measure. Okay, so first note that this map is actually subjective. Okay, why is so? Because of course, like for every partial order, there is a pair which contains a partial order, some linear order. Exactly because of that, because of the order extension principle for arbitrary sets. Okay. So this map is actually subjective. So like we don't have some stupid obstacles for lifting of the measure. So maybe it's possible all the time. Okay. What we can say definitely is that if G is amenable, and who here knows what's amenable group is?
I think almost everybody, but our tradition to remind the definitions. There are some.
Okay, so one of the ways to define an amenable group is to say that a group is amenable if for any action, let's say countable group is amenable if for any action on compact topological space there is an invariant measure. Okay, like one good way to define it. And so what we can do actually, we can show that, and it's in the exercise, that if G is amenable, then we have I will have some property. Okay. And why is so? Because taking very actually even like very general results. So actually, if we have any factorization of actions of compact sets, which is like such as the image is which is surjective, then we can with the measure. So why is so? Take an invariant measure here. Take all the measures. So there are actually some measures which project here to this measure, and they form a compact set, and then take the they form a compact set, in which set we kind of act by G, and then we take the invariant measure, take the barycenter, and what else? We have the. But yeah, basically it's a trivial consequence of amenability. This property for amenable groups. Which is, yeah, which begs the question, what happens if group is non-amenable? Yeah. Okay. Kind of what happens if the group is non. Hard question. Maybe not hard. The first kind of result in the opposite direction, and in some sense it was like a very definitive step in the definitive direction, was the result by Mirovich, Glasner, and it's EU Glasner actually, because there are too many Glasners, so we should distinguish. And Rankin. So Mirovich is one. With one notation. And so what they prove that actually there is a concept to this property. So there is a group, there is a certain group for which we do not have this IRO extension property. And the group is actually, the counterexample is actually, so to have a counterexample, what we need to have a certain measure here which cannot be extended. Okay. And this counterexample actually is a delta measure. So it's actually a partial invariant order. Okay. And this partial invariant order is, so the group is SL3Z. It's a group of matrices 3 by 3 with integer matrices of determinant 1. And in order to define a partial invariant order, we actually need to define the cone of positive elements. It's like there's a correspondence between those guys. So the cone, and for a set to be a cone of positive elements, we need it to be a subsemigroup which doesn't contain the identity. Okay. So what is a subsemigroup? So we have our matrices. We consider the matrices of the form identity operator plus some matrix which has all non-negative entries and some at least one strictly positive. Okay. So we consider elements of this form. Okay. So in particular, there is something like this. Okay. Like all the, we can put one diagonal. And so, sure, we'll check that this is actually a subsemi-group, blah, 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 that it's, yeah, just subsemi-group, which doesn't contain the identity. And from this, we can actually get the partial order just by kind of dividing two elements. We can check whether they comparable or not. So, yeah. So this is their example, counterexample. And anyone wants to settle the question for all non-amenable groups, but it only settles for one. This may be maybe for not for one, actually. For one. Actually, if you have a certain group G, and it contains a subgroup for which we have a counterexample of this form, like kind of this deterministic counterexample, which is a delta measure, so which is a partial invariant order. Then we actually have a counterexample for this group as well, because if we have here an extension property, when apply what we can do, we can apply extension property here, then just restrict the order there, and we get the extension property on this group. Okay, so actually any group that contains this subgroup is a counterexample. Okay, so now what we also can try to do, so for example, we have some group, I don't know, we denoted F, I don't know for which reason. And this group factorizes into SL3C. Yeah. There is a way actually to compare, if we can compare elements, some elements in here, we can actually compare some elements in there, just take their values, in the homomorphism, and compare them. Okay. Yeah, maybe a good idea. And so maybe we have something like this. So assume that okay, F and G are groups, and we have factorization F, G, like factorization onto. So kind of proves out the trivial factorization. Then maybe if we have, if G doesn't have IRO extension property, then F also doesn't. Okay, kind of reasonable conjecture, maybe. Why not? Maybe we can try and second bullet. We okay, let's F be not some abstract F, but be a free group on two generators. And we say something like this. Like we take any G which is non-amenable. And maybe G should contain F as a subgroup, the free subgroup, okay? Maybe why not? And okay, so what it gives us, we kind of actually have a proof, at least one. Yeah. Like you see, so we have like all the heavy lifting was done by these guys. Okay, so then we have a counterexample for two. Then we put it to any non-amenable group. Yeah, it's kind of the plan. But there are two flaws in the plan. So this statement is actually incorrect. Okay, so the problem, this statement is incorrect. And for this statement, I actually don't know whether it's true or not. Like right now, I don't know. But nonetheless, I would like to claim that this plan actually works. Like maybe kind of in a different way, but it works. Okay, so it's a good plan, so we need to fix it. Okay.
So if you replace contain as a subgroup, if you replace subgroup inclusion by this with this property of having a translation-like action,
What do you mean?
you act by permutations at finite superdistance.
Okay,
From the identity.
I will explain what happens. I have a solution, so yeah.
Because then two is true.
It's not the okay.
It is true that every non-amenable group contains a translation-like action of F2.
So what I actually use a variant of this statement which holds true, but which actually uses ergodic theory. And the statement is a theorem by the New lines. Like this, and it goes as follows. So there is for any G non-amenable, there is an action. Actually, it is kind of a maximum Bernoulli reaction, but it doesn't matter right now. There is an action on a certain space, on certain probability space. This action is essentially free, meaning that for every element the action is free. For almost every element is free. The action is free, and such that there is actually an action of F2 on the same space of the free group on two generators. These with orbits of this action being also essentially free, and such that orbits of this action are contained in the orbits of this action. Okay, so kind of we in some sense embed F2 into G, but in some kind of twisted convoluted manner. Okay. Okay. Or in other way, we can think about this, like we can say it's a bit differently. So to every action, we actually can associate equivalence relation, the orbit equivalence relation. So we have first orbit equivalence relation considered to the corresponding to the G action. So two elements are equivalent if they are by the same order or orbit. And another orbit equivalence relation, which corresponds to the action of two. And this equivalence relation is actually strictly just a subset of this equivalence relation. Okay? So, or you can say that elements equivalence class of this equivalence relation splits into the equivalence class of this relation. Okay? And so in this sense, we have an embedding, but the problem is like kind of what is the relation? Like this statement was formulated for groups and for certain objects on groups. So it turns out actually that we can define a similar. So equivalence relations are in a way a generalization of groups. So we can consider actions of equivalence relation. We can consider which are also called kind of extensions of equivalence relations. Like it's another term, but you can actually think like about actions of equivalence relations, which are in some way just actions of the group way of the equivalence relation. Okay. Another thing we can consider representations of equivalence relations. Okay. So they're actually in some ways are now very, very analogous to groups. And so what we can try to do, we can try to develop, we can give a similar definition. We can define an order extension property for equivalence relations. Okay. And we can actually prove the following. So I will not give the definition right now, maybe I won't have time, but we can define the order extension property for equivalence conditions, okay? And we can have, we can actually prove some limits. So first, suppose G acts on some probability space V, and this action is essentially free. It's probability measure preserving action. And take the orbit equivalence relation of this action. So as I said, we take two elements X and Y are equivalent precisely if Y is equal to Gx for some X, for some G. Okay. Then it turns out that actually G has IRO extension property. Precisely then when XE, then our equivalence relation has the IRO extension property. Okay. So what is important for me that actually I can take absolutely any action, and as soon as it essentially free and probability measure preserving on a standard probability space, then the generated equivalence relation has the invariant random order extension property, even only if the group has the invariant random order extension property. Okay. So now also, remember here we have this argument that basically if this idea if the group if we have a counterexample, so we cannot extend all the invariant random orders for a subgroup, then we also cannot do this for the whole group. Okay.
So just to make sure I follow,
Yeah.
Extension and so on for relations is you want to split E as D, disjoint union D inverse in a measurable way? What does it mean to order a relation? Is it that you cut it in an antisymmetric plus its inverse?
Okay. So maybe you need to definish what you are actually asked. What is it? What is this property? Yeah. What is the arrow extension property? What's the idea? Okay. So
Well, what is the partial order which is E invariant?
okay. Yeah.
Am I the only one?
Good. Okay. Maybe I'll just finish this one like 1 minute, like and I will return to this. So was lemma 1 and lemma 2 is that if we have a space and two equivalence relation E1 and E2 like countable for our equivalence relation, let's say. Probability measure preserving. I will not tell you what it is, but kind of equivalence relation which come from probability measure preserving actions. Okay, we have two equivalence relations, and E2 is a subset of E1. Okay, so two equivalence relations on the same space. Then if and assume that the bigger one is so-called ergodic, doesn't like a technical thing, but doesn't matter much. Here. Then we have the following. If the bigger equivalence relation has IRO extension property, if as IRO extension property, then the smaller one does. Yeah. What does it mean together with lemma 1? So together with lemma 1 and together with W line theorem, we get that if we don't have the invariant random order extension property for F2 for the free group, yeah, then we consider this construction by Gaboriau lines. Consider the corresponding equivalence relations. Okay, maybe should here, yeah. So that's this is the big equivalence relation, which this is a small equivalence relation. Here we have invariant random order extension property, which is, as we said, equivalent to the invariant random order extension property for the group.
I think it was correct before.
Okay.
It was correct before.
Okay, sorry. I think I don't think. Okay, now I'm speaker on. So okay, anyway, so we have assume that we have invariant random order extension property for our non-amenable group G. Then we have invariant random order extension property for the corresponding equivalence relation. Then we have the invariant random order extension property for the smaller equivalence relation, which implies that we have invariant random order extension property for F2. So this means that as soon as we have a counterexample for F2, like any counterexample, we prove that for all non-amenable groups, there is a counterexample. There is we do not have the invariant random order extension property. Okay. Okay, so and one more word about like the general outline of the proof. Like this, despite we cannot prove this right away, like for general situation, what is actually possible is to take this construction by these guys and just kind of manually lift it. So we have any factorization of a group onto a self-Z. We lift their counterexample, their order, and it turns out, well, if we follow the proof that actually works, we can prove that actually for this group also we don't have. It also forms a counterexample for this group. And of course, we have a factorization from 2 to a self-Z, yeah, like onto. And so we kind of have a counterexample for F2. Okay. Now, return to a question about what does it mean actually? So it is a bit tricky. So what we do construct, we have a space and consolation. Okay, we define kind of a functor. So the order of xt is we want to define a new equivalence relation on a new space. And of course, first we define the space. The space would be the space of 4 pairs, x and order, okay, where x is in our initial space x, and order is a partial order on the equivalence class of our point. So kind of over each point, we put the fiber of all the possible orders. Over each point, we put the fiber of all possible partial orders of its equivalence class. Okay. And what is equivalence relation? Okay, so this is space. So this kind of goes here, in some sense, corresponds to this guy. So we want to define an equivalence relation. So we say that x and x1 and order 1 is equivalent to x2 order 2 if first x1 is equivalent to x2. Okay, so this is a point from our initial equivalence relation. Okay, and then since these are points from the same equivalence relation, then their equivalence class is the same. And so we say just we require that the order is the same, is just the same order. Okay, we define kind of, and so kind of what we get now is that we have our equivalence relation xe, and we have its extension, as I told before, that we can kind of have analog of action, which is extension, p ort of xe. And this is what is kind of called class bijective extension. Okay, so kind of it is bijective on equivalence classes. So we have natural factorization because we can just forget about this second coordinate, and we have like homomorphism kind of thing. And in the similar fashion, we can define the t ort of xe, yeah, and also ort x of xe. And so what we get is we have the following kind of factorization power. Ort x of xe factorizes to p ort of xe and factorizes to
xe.
xe, yeah. And here we also have a measure. And so we kind of, our extension property is the following. So we actually want for any what is called invariant measurement here, which factorizes to the natural measurement here. Like it's actually like, I didn't say that there is a measure, but there is a measure. We want for every invariant measure here to be extendable to a measure here, such that it protects here, like in a nice way. And so this is basically the extension property for equivalence relations, and kind of with a little bit of descriptive set theory, we can show that this and ergodic theory can show that these lemmas are this and these lemmas are actually correct, and
Thank you very much. Any questions or comments or remarks?
I have a question not about your result, but about something you mentioned in the beginning of your talk. You mentioned this old result of Rimtula and and you mentioned that there is a Metabelian counterexample. Can you say something about this?
I don't remember which, I don't remember.
But it's torsion here, Metabelian group results.
Yeah. Like, so like torsion, like if we have a torsion, it's too stupid, you know, like to say that no, it's torsion free. Yeah, just a billion by a billion, very one step.
So that property is more algebraic in nature. Maybe.
Yes, of course. So kind of what it shows that this property, invariant random order extension property, is kind of very rare. It only sees at least in this form, it only sees kind of amenability, non-amenability. But that property is actually kind of subtle, like the algebraic property, like the exact extension property is actually.
The synthetic nature of the group, your property seems to be much more reasonable, but still I'm wondering, it might be interesting to look even on other solvable groups, right? So just wondering what can happen.
Yeah, also a kind of interesting thing is to think about other structures, not necessarily orders, like you can think about any first order structure. them.
No more questions? Well, thanks, everybody.
Maybe we can tell already even online, we know the dates of our next meeting, right? So in the next one in November,
November 13th, yes,
November 13th.
on a Wednesday.
Days, November 7th, Wednesdays out.